So today we will continue chapter 9 and we will look at some examples which are different than what we have done last time. So in the previous cases what we did is when we look at this sections of the members, what we did is we just write our stress function like this boundary by using the boundary product of these lines. And for example, for a rectangular cross section, a good stress function would be equal to k times x minus a, x plus a, y minus b, and y plus b. So basically the four lines of the boundaries of a rectangular cross section. And we know that this will be equal to 0 on the boundary. So this will be a good guess for us to start with. But the problem is when we look at the governing equation, okay, and if you plug this number and you find delta square phi, what you will find is you will get this function. And this one should be equal to minus 2 times mu times alpha for all x and y, and it's clear that it will not be satisfied. So this is why in this case this stress function did not work to find a solution. So which means that in this type of questions there are some cross section which it works. So you just write the boundaries, and then if you write your stress function k times those boundary equations, it will be equal to 0 on the outside, so it will satisfy that requirement, and then it will also satisfy this governing equation, which should be equal to minus 2 mu alpha. But in this case, for example in this rectangular section case, it does not. So we need to find another method to solve this type of questions. So what we will do is, so since we cannot use our previous method, we will say that, okay, what about we assume that our stress function has two parts. One of them is a homogeneous part and one of them is a particular solution for the non-homogeneous part. And then, so what we can do is, so we can assume that, for example, in this case, our stress function will be so when you put in the governing equation, it will be equal to 0, okay? And then I can also select a particular solution which will satisfy the requirement of the governing equation, okay? And this particular solution we will select as phi p xy is equal to mu times alpha times h square minus x square. And this one, it kind of comes from the membrane analogy, and we will also see it later on some thin rectangles. So basically this will satisfy the boundary conditions on these two sides, okay? But importantly, if you take this particular solution, okay, and if you take the delta square phi p, then what you will see is you will get this minus 2 mu alpha. So this is what we were missing last time, okay? So I know that if I take this particular solution, it will give me this value, which my general phi should also satisfy. And then also if you look at the boundary conditions, so at a, for x is equal to a and x is equal to minus a, so it's equal to 0. So this is also, if you remember, this was a requirement for our phi. It should be 0 on the boundaries. So if you look at the boundary condition on when y is equal to plus b or minus b, what we will find is, so this particular portion of the stress function, it will result in this value. Since there is no y, you will get the same function, okay? So and at the end, I want to use my stress function phi, and it will be a combination of homogeneous and by particular solution. So which means that for the homogeneous solution, what I need is, so when I take this del square of my homogeneous stress function should be equal to 0, because when you combine this one and my particular, okay, which is here, it should end up with minus 2 mu alpha. So it's when you combine them, it will satisfy the requirement. And here I know that when I combine these two, my at the boundaries, I should always get my stress function 0. So when x is equal to a and minus a, it's 0. So which means that in my homogeneous stress function, it should also be 0. And here at point B, so this one results in this function, which means that for my homogeneous function on that one, they should end up with the minus of this function. Okay, so which means that when you combine these two, they will be equal to 0. Okay, so if I define these two functions as this, okay, and if they should have this, for my homogeneous case, it should have this parameters. Okay, so the del square phi h should be equal to 0, and when x is equal to plus or minus a, it should be also equal to 0, and when x is equal to plus or minus b, it should be in this form. So if I can find this stress function, then I can just plug it here and combine it with this one, already find it, and then I can get my stress function. Okay, and in order to find it, what we will use is we use separation of variables. So I will assume that I can separate stress function, homogeneous stress function, as x and y components. Okay, and this one will be only a function of x, and y will only be a function of y. Okay, and the first requirement is, so delta square phi h should be equal to 0, and if you do that, you will end up with these two equations. Okay, and from here the solutions are given like this. Okay, so this is my x function and this is my y function. Okay, and then when you look at this question, what you see here is we see symmetry. Okay, so from there, actually you can assume that this a and c will be equal to 0, so you don't need this sign terms there. Okay, and then, so this was the first requirement, so I will assume that a and c are equal to 0. So I have b and d, I need to find them. And in order to find them, I will look at the boundary conditions. So first one is, I know that when x is equal to plus or minus a, my phi should be equal to 0. Okay, and from there, you can find that your lambda should be equal to n pi divided by 2a, and you can select the n's there. And then when you do that, then it means that I can write my stress function in this form. Okay, so after you know what's your lambda, you can just replace it there, and basically when you multiply this, it will be a constant times a cosine term and cosine h term. Okay. And then I have one more condition. So I also know that when y is equal to plus or minus b, my stress function should be this value. Okay, and from there I can also find that this constant bn, which is given by this equation, and then if you combine all of them, then this will be your stress function. It seems a little bit complicated, but so I have this particular type, and then I have this homogeneous part given there. Okay, so this one should satisfy all my requirements. Okay, it should be 0 at the boundaries, and then when I also find the delta square phi, it should be equal to minus 2 mu alpha. Okay, all right. And then after you find your stress function, then you can get your stresses. So these are how our shear stress is defined. Okay, and if you just take the derivative with respect to y, you will get this equation. If you find tau yz, and if you take the derivative with respect to x and you put minus, you will get this equation. Okay, and then when you look at these equations, and so if you want to find where your maximum is, so if b is larger than a, what you will end up with is, you will end up that your maximum shear stress occurs at x is equal to a, and it is given by this equation. Okay, and then you can also find your torque. Okay, and so this is our equation for torque, and if you calculate it, this is the result that you will get your torque. And then if you know your shear stresses, you can also get your displacements, and if you get your displacement, this is how it will look like. So they're a bit complicated, so they're not as simple as the previous cases, but nevertheless, so if you do the integration correctly, this is what you will get. Okay? And then important thing here is now if we plot them. Okay, And if you plot them, so this is the stress function contours, and again we are assuming B is larger than A, and so this is how your stresses will look like. Okay, and then if you remember, this is kind of similar to what we did in the previous cases. Okay, if you and then here, as you can see, the slope, the higher the slope of this contours, you will get the higher stresses. This is why you get your maximum stress, shear stress here. Okay, and if you look at the displacement, this is how it looks like for the case of A is equal to B. Okay, and you will get this symmetry, like 8 zone of symmetry, and if it is plus, it's solid, and if the displacement is minus, it is given by the dotted lines. And the important thing is, if you change A over B, okay, for example, in this case, if you change A over, so this is kind of square, okay, so this is how you look at it, get it. But if you get A over B is equal to 0.5 in this case, you will get a solution like this, and this is kind of similar to what we get for the elliptical case. So again, so when you get away from this symmetry, so this is square, so if you get kind of more elliptical, you will get a similar case as we did before. Okay, but nevertheless, as long as you have these two equations, in this equation, so if you can get your displacement, and here you can get your shear stresses, and you can find what's your maximum shear stress if you take the square root of the square of those two numbers. And then what we will do is we will look at a special case, and we will look at a very thin rectangle. So in the very thin rectangle, what we are assuming that A is much smaller than B. Okay, or in other terms, B over A is larger than 1. So if you look at there, so this term, okay, when B is much larger than A, so it will go to infinity, and this term, tangent H term, will go to 1. So which means that if you rewrite your if you calculate your maximum shear stresses and torsion and etc., so this will be your stress function. Okay, so I mean, if you look at this, so this is very similar. This is very similar to what we get for the particular case. Okay, and then if you look at the T max, this is a kind of simpler version, and this is the torque that you can get. Okay, so in these cases, so these values, I mean, they will be very simple looking. So we want to have this hyperbolic functions. Okay. All right. And then also, so this is the result that we get for rectangular cross section, thin cross section. But if you have like composite sections, what you will see here is, so in order to get the results here, what I can do is I can kind of combine my results. I can assume that each of them, they are made of thin rectangular cross sections. Okay, and if I ignore these ends, so I will assume kind of a uniform shear stress. Okay, and from there, for example, if you want to find your torque, you can get it from this equation. Okay, and after you get your torque, you can get your alpha, and if you get your alpha, you can get your maximum shear stress in each region. Okay, but basically in this case, what we need to do is we can use this equation, but we just need to add this A cube times B terms for each section. So another topic is in this kind of torsion questions is what happens if you have hollow cross sections where you have holes inside the cross sections. So similar to the outside, what you will see is, so there will be no tractions on this inside surfaces as well. Okay, and so there will also no tractions on the outside surfaces. And from this, what we can conclude is, so we can conclude that the stress functions on the inner surfaces, they should be constants. So For outer surface we set it equal to 0, but for inner they just need to be only constants, and the displacements can still be found by using this equation given there. So since the stress functions inside are constants, okay, and we can select any constant value, okay, and again don't forget that generally we take the stress function 0 on the outer surface, but in the inner surface we can select any constant value, okay. And then if we selected this constant stress functions, and it results in single valued displacements, okay, and from there you can also find that. So if you want to find your shear stresses, so we can use this equation, okay, and since our displacement will be single valued, and if you add them for the whole surface it should be equal to 0, and from there we can get this equation, okay, and which means that the addition of your shear stresses on this surface should be equal to 2 times mu alpha times A1, okay, and A1 is the area enclosed by S1, so the area inside the area of this hole, okay. So as long as you know it, and you can get this equation given there, okay. And so when we selected this, we need to make sure that this phi value is selected carefully so that it will be a constant, okay, and then it will result so when it's constant, and then it can result in this relationship. And if we can satisfy the boundary conditions, then we can find that our result, the torque, will be given by this equation, okay. So this is what we got before. So if you don't have this hole, so we were using the whole region, okay, and now what we are doing is we are using the region, so between here, okay, for this equation, and we are adding kind of the torque that is kind of on this surface, okay. And if you have more than one hole, then you can still use this equation. Okay. So basically what this one tells you is, like, if you assume, like, like this area, so normally if it was closed there will be a torque carried here on the surfaces, okay. So we add the remaining region to that kind of torque that might be there without this hole, okay. All right, so we will solve some examples to understand this a little bit better. So first one is, as we did for the solid cross-sectional, we will look at the elliptical section, and so this is what we started with this outer elliptical, and now we will select something smaller, okay, inside of this our initial elliptical region. And now we have and normally don't forget that when we selected our phi, okay, for the outer region, we selected that phi must be 0, and from example 9.1 we find that we can select our phi as k times x squared divided by a square plus y squared divided by b square minus 1, okay. So this is how we select it, so that it will be 0 on the outer surface, and when you plot the stress function contours you will see that you will get stresses like this, okay. And when you look at this stress function contour, what you will see is if you cut it somewhere, okay, so this stress contour is same as this lines, okay. So which means that if you remove the inner core, okay, so there is no stress in the normal direction, so the stress is only in the tangential direction. So we can just simply cut it out here. Okay. So this is why when we are trying to find this hollow section solution, we will just remove this inner core from the solid solution. So if you look at the inner boundary, so what you will find is, so now I want it to be a constant, so it's k times. So before, what we did is, if we look at the outer, for example, it was k times this value minus 1 is equal to 0. But now I don't want it to be 0, but I want it to be a constant. So I can say that this is, I want it to be a constant value. Okay? And then when you look at here, so if I rewrite this, and now I have x squared divided by a squared plus y squared divided by b squared. And if you look at this equation, so for the inner circle, x squared divided by a squared plus y squared divided by b squared will be equal to k squared. So I can replace this as k squared. So which means that my constant should be equal to k times k squared minus 1. Okay. So which means that if you write your phi, okay, and we know our k from the previous case, I can write it in this term. So this will result in a constant value. Okay. So all I did is, instead of putting 0 here, this time I put c for the inner circle, and I just replace this term with k squared. Okay, and then from that I get my new stress function for the inner boundary. Okay. So that's all I need to do. So and for the torque, now I know my value. So if you use the outer, so when x is equal to a, so it's elliptical with a and b. Okay, and now since I kind of cut the inside elliptical, I will just say that it's minus phi times, now my dimensions are Ka and Kb. Okay, so if you do that, this is what you will end up with. So this is my torque for this hollow cross section. And then again, if you want to find your maximum stress, it will be when x is equal to 0 and y is equal to plus or minus b. Okay, and in this case, this will be your maximum shear stress. Okay, and here, since my torque has this value, my shear stress will also have that constant here. Okay, so which means that if you look at this case, okay, and so again in this case a is larger than b, so this is why you get your maximum stresses on this part. And similarly, if you have a hollow cross section, so basically I just cut it here. Okay, and so if I'm calculating my torque, I can just calculate it this way. Okay, or if you want to do it in the more by using the equation here, you can also use this one. Okay, so you can still use this equation, all right, and you will get the same answer as this one. Okay, and again, my maximum stresses, shear stress will occur at close to the y equal to plus or minus b, and it's given here. All right, so this is a kind of specific example where we look at the hollow elliptical cross section, but the idea is same. So normally we only use the outer value where our stress function is supposed to be 0, but now for the inner surfaces we also need to find a stress function, but this time that stress function should be equal to a constant. Okay, and as long as you can find it, then you can write your phi, and after you find your phi, you can just continue solving the problem. All right. So now what we will do is we also look at a special case where we have very thin walled tubes. Okay, so in this case, let's say you have this shape of the cross section. Okay, and this time what we are assuming is this thickness is very, very small. Okay, and when we assume that this thickness is very, very small, and then what we will assume is we are looking kind of membrane. Okay, And when you look at the membrane of this case, okay, so what we'll see that if you had a membrane, this will be, it has deformation, okay. And so, and then, so since this is the membrane deformation, I can use this analogy to determine my shear stresses, okay. And here, this is kind of from A to C, it will be my phi naught, okay. And if you want to find your shear stress, okay, so you need to find the slope, and basically you can need to find the gradient. And since this is almost straight line, I can assume that my gradient, or basically the slope, does not change. So this is why my shear stress is equal to my phi naught divided by thickness, okay, since I'm assuming that this is a straight line. So from there I can get my torque, okay. So, and then my torque is, we just find that it's given by this equation, okay. And then this is, so when you calculate this, so basically you need to do so this is kind of the area, and so if you know this area of the section, okay, so you can approximate this value as 2 times area times phi 0 divided by 2. So basically it's the area times the kind of the thickness, okay. And then, so this term is area 2 A0, the area of the inside of the inner boundary, so area inside, okay. And if you combine this, you can get this formula, 2 times phi 0 times area of the area enclosed by the center line. So I mean, they will be very close to each other, but so this is the area enclosed by the center line, because I have the inside area, and then here I have this kind of this area times phi 0 divided by 2. Okay. And then if you combine those equations, so from here I can get my phi naught in terms of torque, and if you just plug it here, what you will find that your shear stress is equal to your torque divided by 2 times area enclosed by the center line times thickness. And if you want to find your angle of twist, so what you will find is I can use this equation, okay. So I can if I integrate all my shear stress along this on the kind of the surface, I can write this equation, okay, and from there I can get that my angle of twist is equal to my torque times the length of the tube's center line divided by 4 times area enclosed by the center line square, mu, and times thickness, okay. So from here I can also get my angle of twist in terms of torque, okay, and from this equation I can get my shear stress in terms of torque, okay. So this is what I can use for thin wall tube sections, okay. And so if you look at this equation, all you need to know is you need to know your torque and the area enclosed by the center line plus thickness, okay. So this is what happens if you, the previous case was when you don't have, like you have these enclosed areas, and then what happens if you have a cut, okay. So what happens, for example, if you want to find your shear stresses in this region, okay. So when you have a cut, then it becomes an open tube, and then it significantly changes your stresses, stress functions, and etc. So if you want to find your stresses in this cut or in this open tube, so basically this is more of a case of thin rectangular solution, okay. So if you want to compare them, so this is the result we just got from the closed tube. So if you want to find your shear stress, this is the equation, okay, for a closed tube. And then for the open tube solution, what we need to assume is we just unfold this, okay, so it looks like a rectangular cross section, okay. And then in this case, if it's a rectangular cross section, these are the equations we just get, okay. So I find my maximum shear stress at this areas, okay, and then the torque is given by this equation. So if you combine these two, you will get that your shear stress for open tube is given by this equation, okay. So it's 3/2 times torque divided by A, so basically half of your thickness, and the area of this section, okay. And if you combine those two equations, so if you want to, for example, if you take the ratio of your shear stress for open tube to your shear stress of the closed tube, this is what you will get, okay. And then so here, so they will cancel each other, and I know this A is half of my T, so if you combine this, it's almost 6 times area of the center line enclosed by the center line divided by the area of the section, okay. And in this case, what I know is this area is much larger than the area of the section, okay. So which means that in this case, my shear for open tube will be much higher than my shear for closed tube, okay. So stresses are higher in open tube than the closed tube, okay. So which means that if you apply for the same torque, this is what you get. So which means that since shear stresses are much higher in open tube, it will fare much easily. So which means that for the same torque, so your closed tube will be much stronger. So you want it, so if you design this, it's much better if you close that gap and you end up with the closed tube, okay. So this is just a simple comparison, so of this just simple 10 volt rectangle and versus the 10 volts hollow circular hollow cross sections, okay. So since I mean, you can easily see that for the same torque, the shear stress in open tube will be much larger than the closed tube, okay. So this is why this design is not that good. So if you have a cut, it's not a good design.